Field interactions of parallel current carrying wires. Yeah, field interactions of parallel current carrying wires. So what I mean by this is that we've got two wires, wire 1 and wire 2, and I'll try to draw them somewhat three-dimensionally, both coming out of the page, and I know that around each wire there might be a magnetic field, and I could talk about that using a right-hand rule. So in this case, both coming out of the page means the magnetic field would be oriented counterclockwise around each of them. So around this one, it would be a magnetic field like this, and around this one, a magnetic field also like this. And we could talk about having I1 and I2, that's the current in each wire, each inducing magnetic field. Now at some point, as you get further and further from the wires, we said the magnetic field continues to exist, it might just get weaker, and at some point I want to say that, look, this current carrying wire produces a magnetic field so that there could be a magnetic field line that coincides with the center of this wire. You see what I mean by that? I'll draw it as a green line. Dotted green line. This is the magnetic field due to wire 2 as it passes through the center of wire 1. Yeah?
So do magnetic fields ever stop?
Well, this is if wire 1 didn't have current flowing through it. You're right, they would cause some warping to one another.
No, I mean, like, do magnetic fields ever stop, or do they just continue growing weaker and weaker?
Oh yeah, they keep on going weaker and weaker and weaker until you
So
can never
we're
measure
feeling
them.
magnetic fields from, like, China right now?
I don't know that I'm feeling them.
But, like, they're around.
Yeah, I don't know. Well, it's like saying that you're slightly attracted to somebody in Peru. According to Newton's universal law of gravitation, yeah, I am slightly attracted to somebody in Peru right now. But do I really want to calculate it? Yeah, long distance attraction is hard. The dating world. All right. So obviously the other current carrying wire would find itself in the presence of the magnetic field from current carrying wire 1 as well. In any case, it looks a little bit like a Venn diagram or like a really loopy googly eyes. But these two wires find themselves within the magnetic field of the other wire. Yeah?
So are the big dotted lines the magnetic field?
Well, the solid red lines are the weak magnetic field. The big dotted lines, I just wanted to show them as big and dotted to differentiate. They're also the magnetic field, but just at a further distance away. And so this big dotted line belongs to I1. And this big green dotted line belongs to I2. And this big dotted line, you know what, I could call it B2. And I could call this one B1. I2 finds itself inside of B1, or influenced by B1. And I1 finds itself being influenced by B2. Okay? So if we wanted to draw this in a little bit more simple way, I could say, all right, so here is I1 coming out of the page. Here is I2 also coming out of the page. And at the point where I1 is, there would be a field, and we can call it, I'll use different colors. I should have made the colors match. We can call it B2, because I1 finds itself in the presence of B2, and B2, at this point right here, happens to be oriented down. I2 finds itself in the presence of B1, which at this point, if we follow the contour along, happens to be pointing up. Oopsie. B1. Now I want you to, well, another thing is the fact that these two are separated by a distance r. Okay, so they're separated by a distance r. And before we really go any further with the math, I want to talk about a right-hand rule. If the current's coming out of the page for this wire here, and the magnetic field is oriented upwards, what direction is this wire going to get forced?
We're going to get forced
Inwards, yeah. This one here, the magnetic field is oriented downwards, and the current is pointing out of the page. It's going to get forced inwards. So if two current-carrying wires are side by side, what's going to happen to them? Yeah, they'll get attracted. What do you suppose would happen if this wire was pointing into the page and the magnetic field was pointing up? Let's see. Yeah. Oh, I'm just putting my hand in front of the camera at this point. They would get repelled, though, yeah. Reach your hand in front of the page. You can see that if this current-carrying wire is going into the page, this one would get repelled out that way. And if this one had a current-carrying wire going into the page, then it would have created a magnetic field that was pointing up, and this one also would have gotten pushed outwards. Okay, so current that's going in the same direction, side by side, is going to attract. Current going in opposite directions, side by side, is going to repel. Anyways, and then you could put that in writing if you want to as a nice little rule. Current going in the same direction will attract because of this idea. What we'd like to do is find the force of attraction, though. So I want to remind you of a formula that was from your reading, and it was that F equals I L B times sine of theta. And if we want to talk about the force that's acting on current or wire 2, let's just talk about the force that's acting on wire 2 so that we can sort things out here. The force that's acting on wire 2 would be equal to the current going through wire 2 times the length of wire 2 that lies within this magnetic field times the magnetic field that's being produced by wire 1. Okay? And we know that we could find, and I'll set it up as a second formula, we could find the magnetic field due to wire 1. Oopsie. We could find the magnetic field due to wire 1 using the formula mu naught times I over 2 pi r. We're talking about the current going through wire 1 and the radius between, well, really, the radius between wires 1 and 2, but we can just call it R1. Okay. So if I really want to find the force of attraction, or the force of repulsion in this case, sorry, force of attraction in this case, between these two wires, I can sub equation 2 into equation 1. Yeah?
So the force is I, L, B. What is the L?
The length of wire that finds itself within the magnetic field. Yep. Sub 2 into 1, and we end up getting the force of attraction on 2, or the force of 2, or force on 2. You could say force of 1 acting on 2, but the force acting on 2 is simple enough in this case. There's enough going on here. Force acting on wire 2 would be I2 times the length of wire 2 that finds itself in the magnetic field being produced by wire 1, which is mu naught I1 over 2 pi times the distance between these two parallel wires. And that force could be calculated in the same way for wire 1. Oh, sorry, times sine theta, yeah. Times sine theta, you're right, it is times sine theta. Now, in each of these cases, we're going to make an assumption that these two wires are parallel to each other. I'm not going to make non-parallel wires in this course, but you're right. The sine theta comes into play when the wires are not necessarily parallel to each other. We're only going to deal with parallel wires in this course, and so if the wires are always parallel, in this course that is, the sine theta simplifies out to just being 1 because the theta will always be 90 degrees. But you're right, in future courses, future studies, that may not be the case. I'm sorry, I made my own simplification without explaining it. Yeah? So we have I2 and I1 both included in this equation. Some people like to reorganize this to get the I's by themselves. I don't know why, but sometimes it just feels better, I suppose. I2 times I1 times mu naught all over 2 pi r is equal to, I know, F2 over L, because some people like to express it as a force per unit length of wire. Okay? So the amount of newtons that would be felt on a wire per meter of wire that's present in a magnetic field.